Yeah, like the hours, you see the timing.
How do you know it's full?
Well, 6 hours.
It's the
Seven.
time,
Yeah, it's
the
the time.
timer ready. Okay. You can equip Andy with the microphone.
So, yeah, this is
Andrea,
way.
what are the names of all the organizers?
There's
You and Dario?
there's Andrea, there's Laura, and Simona.
Wait, Dario, Andrea?
Dario and Andrea are here. Simona,
Yeah.
I haven't seen. Simona Speciale. Yeah. Ah, yeah, and Sabrina. But
This is not your Simone Speciale.
it's not here.
Is that okay? The size of the mic?
Um, seems a little small.
It's too small. Okay.
Yeah.
Let's try this.
You wouldn't know if he were, but
He
you
would.
you
I
wouldn't
don't know.
know. Uh,
He's in cover.
I guess, yeah. Does it look right? Okay.
So this one you can like put it on the pocket.
Yeah. Great. Andrea, if we can raise that, maybe there's a little more light on the board or not.
Okay.
Wait, Laura's an organizer or not? Laura,
Andrea,
Andreas,
Andrea,
Andrea and
two
Andreas.
Andreas, Dario, Simona, Laura, and me.
Yeah,
Oh, Sabrina.
and Sabrina.
Okay, welcome everyone to day two. Let me first start with a few announcements. So there is a dinner on Thursday, and if you haven't signed up for it but you still want to, there's still a chance, but please do this today. On Wednesday, there's a guided tour to Florence. There's a sheet here where you can sign up, so please do that if you're interested. And then an encouragement to this afternoon speakers, please send the slides. We still don't have them and need them. Okay, and then we can get started. So we are extremely happy to have Andy Strominger kick off day two, and he's going to talk about algebras in AdS4. Please take it away.
Okay, thank you. I'd like to start by thanking the organizers, Andrea, Andreas. Uh, what? But there's also an. Oh, you don't have an S. Oh, okay, okay. Andreas squared. Um, Laura, Dario, Sabrina in absentia, and Simone in absentia. Um, I wasn't here for the inaugural conference like Massimo, but I was here that year, and it's an amazing place here. Conference centers form and they disappear, but this one really seems to have staying power. So there's some good magic here. It's really working. I've really been enjoying myself. I am going to talk about work in progress with three students, Ahmed Sheda, Adam Tropper, and Hongji Wei. Um, we've questions, which I'll talk about, and our work also, I think, raises some more questions. But before it's mostly going to be a sort of specialized talk, but I'm going to start with just trying to put it, probably spend 20 minutes just trying to put it in general context. So the motivation and the subject of this workshop is to try to understand holography in the real world, which in some approximation is four-dimensional Minkowski space, and in a finer approximation would be four-dimensional de Sitter space, and the kind of challenges we have to overcome to get out of the AdS and into this kind of are clearly quite considerable, because there are still fundamental mysteries about how we think about holography in these more general concepts. Now, there are a number of approaches that have been being pursued, and we've heard about most or all of them. The first kind of approach goes under the general name of top-down. And of course, there's been notable successes in sort of using twisted topological string theories by people like Biddleston, Castallo, Paquette, Sharma, and a whole group of people. These are unrealistic theories, but ones which you can have really great mathematical precision. Another top-down approach is just ordinary string theory, and there's been much less work, Stieberger and Taylor, but I think there are also, I think that's largely unexplored, which there could be done. There's kind of enticing relationship between the string world sheet and the hoped for celestial conformal field theory that we clearly ought to be understanding. Then there's the bottom-up approach. And this also comes in several strides. So the bottom-up approach is you have some general idea of the framework, how holography should work. You constrain it by principles and various kinds of symmetries, consistency constraints, and try to work from the bottom up to understand what holography would look like in the real world. If we had discovered that the cosmological constant were negative instead of positive, which isn't incredibly hard to imagine, I think there would be many people now trying to understand what dimension operator the electron and the muon correspond to, and what sort of conformal field theory could accommodate that. And that is very different from what most of AdS is doing now, where you start with some complete, exact laws of nature and try to get everything all at once, which is great if you could do it, but very hard to, imagine, or at least for me, it's very hard to imagine that at this point in history, we're going to get a complete description all the way to the Planck scale of some exact conformal field theory or holographic dual of our world. And so there are different kinds of bottom-up approaches. There's the celestial approach and the Carolian approach, which of course are related. And as I said, this endeavor doesn't try to get complete laws of physics. Rather, you get just some partial matches between things on the two sides of the dual. And an example of that, and I've been involved in, was Walker's talk, found a field theory, a field theory, celestial theory that reproduced the MHV amplitudes. It wasn't everything in the celestial theory gives everything on the bulk side, but just getting pieces of it to a field for how it might work. And then whether to put this as approach, maybe I should just sort of write it over everything. That's a good idea. Twistors. So twistors is some amazing uber speed corner and helping us to whether it's bottom down or bottom up or top down. But it's good for bottom down too. I don't. Okay. So then there's toy models. And probably the most developed toy model is 3D gravity, which has a special feature that it can be obtained as the flat limit of AdS4 gravity, whose holography we understand very well. And we've learned a huge amount from that. As befits a toy model, it doesn't have all the features of the full world. There aren't propagating. We don't have. Is the sound coming out okay? What? I think I knocked it and it went. How's that? It's okay, but I'm not sure it's going to stay. We'll see. Okay. So, but I'm really going to talk about another one, which I've been very interested in, which is four-dimensional self-dual gravity. And by that I mean just gravitons, not adding the other things that make it an integrable theory in twistor space. And this is very interesting because I think there are, it's one of a very small number of consistent quantum theories of gravity. Of course, it has some peculiar features by virtue of its self-duality, but it can be shown, and was shown long ago, that all the loop corrections vanish beyond one loop. And there's a very explicit and intricate formula for the one loop corrections that clearly has a lot of structure in it. It's rational. And we don't have a way of thinking about that. Is there some kind of holographic dual that would reproduce both the tree level and the one loop amplitudes for gravity? And that seems like a simple enough toy model that it might be something we could actually solve in a really explicit way and something from. Now, and just to emphasize it again, it is one of a very small series of gravity in 4 dimensions, which are consistent at the quantum level. Now, 4D self-dual gravity has a simple toy analog, and that is 4D self-dual Yang-Mills, which is really what I'm going to talk about today. And not only am I only going to talk about 4D self-dual Yang-Mills, I'm just going to talk about the tree level theory, but I wanted to put in the context that how this might segue into a better understanding of holography. Now, self-dual Yang-Mills one of the interesting things is that if we take self-dual Yang-Mills on M4, and we do a conformal transformation, and by this I mean a Weyl, there's a map from four-dimensional Minkowski space to four-dimensional anti-de Sitter space, and since the theory is formally invariant, actually, as is the loop theory, as is the loop-corrected theory, if we've understood self-dual Yang-Mills theory on M4, it should at the very least teach us a lot about self-dual Yang-Mills theory on AdS4, and actually we can turn the arrow around. We know a lot more about how holography is supposed to work on AdS4. So if we understand how holography works for self-dual Yang-Mills theory on AdS4, we should be able to do a conformal transformation and understand something about how it works on M4. And so this is such a simple problem, but it really is not understood. And is self-dual Yang-Mills theory on AdS4, and I want to give a special thanks to, is he here? Lionel, for having set me up for this talk yesterday and produced a lot of the material and background. We might expect that it has some dual boundary CF3, and even, however, even the basic question, the correlators, which that CFT3 is supposed to reproduce, have not been written down. And so, though in principle this theory was solved, I guess, by Ward 40 years ago, we haven't been able to write it in this language and in the language that we're using. So that this problem that's been solved in a different language, and Lionel explained much of that yesterday, that we haven't translated into the language that we're using to try to solve holography. Okay, let me pause and see if there are any questions. Yes, Sangmin.
So about this map from the Minkowski-4 to self-dual theory on Minkowski-4 to AdS4, is there an analog of how the map becomes when you go like to near AdS4, or a little bit of departure from AdS?
Probably. Yeah, you mean like a near horizon type of situation?
Yes.
Probably, yeah. Yeah, I think there would be a lot of interesting questions we could do and answer within this subject.
Thank you.
Now, as Lionel told us yesterday, self-dual Yang-Mills theory is controlled by the S algebra and takes a while to write out. So here we have the two generators. We might contract, these are really functions of Zm. We could turn these into functions of, this is kind of a Taylor expansion. We could turn this into functions of Z and Z bar by contracting and summing, but I'm going to leave it like this. This would be a color index. These are some modes of the positive Felicity gauge self-dual gauge bosons, and they obey an operator product algebra which turns into a chiral algebra in the boundary in the context of celestial holography. It turns into this chiral algebra, a very simple chiral algebra. And I also want to stress that this algebra admits a central extension, which Walker and Sruthi and I found a couple of years ago. And it hasn't been discussed so much because in the context of flat space holography, this central extension violates Poincare invariance. But in fact, it is consistent with the AdS algebra. And so one might expect that in doing the conformal transformation from flat, it's an open possibility that when you go from flat space to anti-de Sitter space, that you generate a central term in the AdS algebra. And okay, so we're going to be talking more about that. Now, but in the context of flat space celestial holography, these are soft theorems. This is basically the algebra of this algebra is the algebra of soft theorems. That's how it was discovered. Now, in AdS, there's a mass gap. And so you don't have soft theorems. You can't take things down to zero energy. So one of the puzzles that's been bugging me for a long time is how can, it's a conformally invariant theory, so it should be easy to take it from flat space to AdS, but there's no mass gap in AdS, so how can you have a soft theorem? And this has a possible answer, which we'll give some pretty good evidence for during the talk today. Now, I'm still in the motivation section, and I have to say that a big motivation for all of this was the discovery of this amazing deformed W algebra. So the W algebra is to the S algebra what gravity is to Yang-Mills theory. And this algebra was discovered in the context of, it was rediscovered many different ways, but in the way that I think about it, it was discovered again as an algebra of soft theorems in flat space. And again, you would expect it not to go on to AdS. And I should say it was discovered by these people, a group at Oxbridge and a group at Northeastern. And without AdS, you just have this first term here. That's the ordinary W algebra. But when you add a cosmological constant, it's deformed in this manner. And it was a shock to me that you could, first of all, it's very hard, it has to obey the Jacobi identity. It was a shock to me that there is such an algebra, is such a deformation. And moreover, the beautiful thing that happens, whereas this thing acts on flat space, it has, it preserves a Poincare, has a Poincare subgroup. That subgroup is destroyed when you add this extra term, but instead you get SO32, which is the isometry group of AdS4. So it's very beautiful the way that happens, and this deformation only of the central term of the S algebra is potentially on a similar footing, though we haven't done the calculation in the same way. Okay, so what? Yeah, so nobody has shown. I don't think it's very hard, but nobody has asked the question whether this algebra is this S algebra is a representation of the deformed W algebra. Have they, Malcolm? Have they, Lionel? No, but the question is whether it's if we set lambda to 0 and the central charge is to 0, then the S generators are in a representation of the W algebra. So we could ask whether the deform, and I actually suspect that it would fix C1 in terms of C3 halves. Yeah. Yeah. So yeah, it's a very interesting question. I mean, it better be true, but nobody's. Okay. So what is the general idea? Well, we're talking about a theory which in the four-dimensional bulk has a gauge field. And if that's in AdS4, if we have a local gauge symmetry in the bulk, that gives rise, just by the rules of AdS holography, that gives rise on the boundary to a dimension 2, a conformal dimension 2, conformal primary field, JAB of TZZ bar, which is conserved and generates global symmetry transformations. So what is going to happen? We could now take this JA, and so what we're going to show is true just at some, not for every term, but for one term, that if we take this thing, which transforms, is a representation of SO3 comma 2, the three-dimensional conformal group, and we decompose it under SO3 comma 1, the two-dimensional conformal group of the sphere, which the S algebra transforms under, then JA decomposes under this smaller group into an infinite number of things, which are basically the generators of the S algebra. That will be the relationship between soft symmetries in celestial holography and the familiar global symmetries that we get in AdS4. And we'll show exactly how this works for P equals 1, and we'll get partway to what happens with the other P's. Now, so there are two lessons. All right, there are two lessons I want to draw from this deformed W algebra. One is that we always think of AdS4 physics, the dual, as being intrinsically three-dimensional. But this is really most simply thought of as a two-dimensional algebra, because M and M bar are indices that transform under the representations of SO3 comma 1. the two-dimensional conformal group. So it's kind of surprising that there would be a two-dimensional algebra which would summarize so much about AdS4, because we would think of it as be relating to a three-dimensional algebra. And the other thing is that there is lessons we're going to get is that there is some way of talking about some symmetries which are directly related to the soft symmetries in flat space, even though there is a mass gap in anti-de Sitter space, and we'll see how that works. Okay, now there is both a bulk AdS and a boundary AdS way of understanding these things. And I found the bulk more intuitive, but the boundary easier for explicit formulas. So what I'm going to do is I'm going to spend a page here, which is I'm going to draw some pictures of some geometries and explain what the relationship of these various things are. And then when we're going to write down, although it's possible in the bulk, the formulas are longer. And when we write them, actually go to write things down, we'll go to the boundary picture. Okay, so step 0 is the geometry. So here, there are different ways of relating AdS4 to M4. And here I'm going to use the relationship that was used in a pair of beautiful papers by Chen, Myers, and Riclario, and Pastersky and Sharma. And they do the following. What? What, you weren't on that with Sabrina? I was there. One of Rob's students was also. Oh, your stead. Oh, yeah, sorry, okay. All right, so this is the Einstein static universe, which is S3 cross R. And famously, AdS4 is conformal to, this would be time slices in AdS4, conformal to 2 copies of the Einstein static universe, or we can think of it as the subset of dynamics on the Einstein static universe, which is invariant under Z2 reflection about this line. Minkowski space, on the other hand, looks like this, meets itself around the back. Okay, so that, we can also write that, maybe a little more cleanly, is here we have AdS4, and then we have a Minkowski diamond, which goes out like that. Okay, so now there's been many papers on the construction of conformal primary wave functions in AdS4. And if we're talking about a field with a conformally invariant wave equation, we can extend that to the full Einstein static universe, and we can also extend it, of which the AdS4 is a subset, so we can also extend it to AdS4. So how does that work? Well, suppose we have a wave function phi delta, and the plus or minuses are going to be important here. So x will be a bulk coordinate. Now, importantly, right here is the celestial sphere, z and z bar. Or really, maybe we should think of it, I'm not going to think of it that way. Let's think of it, there's a sphere above every point, so this would be the celestial sphere, which has coordinates z and z bar. So we take a point on the celestial sphere, and we get a solution of the a conformal primary solution of the wave equation, which goes over all of Minkowski space, and where Q here is the vector which points, Q is a function of z and z bar. It's the vector which points to the point on, goes to the point on the celestial sphere labeled by z and z bar. Okay, so this really is a function of z and z bar. Now, we can take this thing, and if we take g goes to omega squared g, of course this can all be written out in great detail. If we take g goes to omega squared g, we can, and we get a new solution of the conformal primary, a new solution of the wave equation, and but we can extend it over all of AdS4. Now, there are several things to say about this. The first is that this thing has branch cuts here. And so we have solutions. We have to say which branch cut we're going on. The two solutions with the two different I epsilon prescriptions. You'll get phases as you cross the branch cut. There'll be independent solutions. There is also a branch cut along here when we extend to AdS4, and we'll have to make some choice about this branch cut, and that is discussed somewhat in these earlier papers. But in any case, we can, depending on how we choose the branch cuts, we can get not infinite number, but several extensions of solutions of the conformal wave equation, conformal primary solutions of the wave equation from M4 to AdS4. Now, how is this SO3 comma 1? So what is the SO3 comma 1 from the AdS4 point of view? Well, here we have time in AdS4, and the SO3 comma 1 is a subgroup of the SO3 comma 2, which preserves a t equals 0. And it acts like two-dimensional Euclidean conformal transformations on the sphere of the t equals 0 slice. So our goal is going to be to take things that transform like three-dimensional conformal primaries, like this current J, which you naturally get in the AdS4 correspondence, and decompose it under this two-dimensional conformal transformation. And the reason we want to do that is because we know at the end of the day, these very nice algebras are waiting for us. So this is hopefully related to Lionel's comment about trying to understand S algebra as living in some kind of CFT3. Now, it's interesting here So now we know how to construct through this procedure, but there's still something else we need to do. Now, draw this picture again. So one way of getting conformal primaries, if we want a conformal primary operator, I'm using capital for the operators, phi plus or minus delta. What we do is we take a symplectic product over some surface of the field operator with the C number conformal primary wave function. That gives the operator that creates a mode with transformation properties. Now, what surface did we use? Well, in Minkowski space, we could use this surface, which, if we push it up to null infinity here, becomes the usual Mellon transform formula. That's not a Cauchy surface. If you choose the right combination of these, there's one that vanishes with several. There's one that vanishes in this region. We could also add in the rest of them. And what we would really be in this context, functions of something. And your work, know that there's a Z2 on the Einstein cylinder, which is rotation by pi, which is exactly what we. So there's a rotation by pi that relates this AdS with this AdS, and that's the shadow. So if we take the field and add its shadow to it, we get something which will obey the AdS boundary conditions. So that would be what you could be doing here. So now we can integrate over. We can take this to be sigma, but this, if we look at it in AdS, we take this conformally transformed field on AdS. That's a bulk integral in AdS. In Minkowski space, we would have pushed that up to scry and gotten a boundary integral. Now we want to push it down to here. And in fact, it's possible to write this integral over there as an integral on the boundary of AdS. And if you're a twistor person, you call that the Penrose-Kirchhoff map, which was written down 50 years ago. And if you're an AdS person, it's the bulk to boundary correspondence. But neither a massless field in the bulk of AdS, you can write it as an integral over the boundary. So at the end of the day now, what is the steps here? We take this phi, this conformal primary wave function, we extend it to the Einstein cylinder, we make it Z2 invariant by adding the Z2 rotation. Then we have something which obeys the AdS boundary conditions. Then we have this integral, a space-like integral. We use the Penrose-Kirchhoff map, and we get something written over now the boundary of AdS. So what have we done through this series of manipulations? We've understood a way to take these S generators. I wrote down a scalar field here, but gauge fields are also conformally invariant. We found a way to take these S generators and write them as boundary integrals on AdS. Now, there were a lot of steps here, and at the end of the day, it's better to simply write down the answer. And I guess I'm going to have to skip some stuff. So that was really motivation to write down the answer and check that it does the right thing. So now I'm just going to present a very general formula, which we derived in this way. You never had to say for if you have a field theory in 3 dimensions, which is acted on by SO32, and you take a slice t equals 0, which is preserved by the subgroup SO31, how do we take conformal fields in 3 dimensions and write them, reduce the representation and write them as an infinite series, as an infinite series of representations under this SO31? And here's the answer. So first we define phi delta chi plus or minus. So basically what we want to do is we want to start with a 3D field. I'm just going to write the formula for scalars, which has conformal weight chi. And I want to write it as decompose it as 2D fields of weight delta, no t. 2D conformal fields of weight delta. And what we need is something which is kind of like a bulk to boundary propagator. But it's where this is the boundary and this is the bulk. So we have to put in the I epsilons. And we're going to continue the formulas to Euclidean space. And then we find O delta plus or minus the 2D field, WW bar, is equal to the integral d squared z dt phi plus or minus delta chi O delta chi. And now if we have an operator, so let's now do a conformal. So now we want to take the generators. There's 6 of them. They're just the ln's and the ln bars. Now we want to take the transformation of this thing we've just defined by this integrating this kernel, and that should be equal to the 3D variation of this with respect to the same killing vectors lifted to 3 dimensions. And it all works out that this is a 2D conformal primary. Okay? So this was just an exercise in representation theory, kind of a complicated one, but we showed that you could take modes of three-dimensional conformal primaries, and now um,
Can I ask a question?
yeah.
What is the range of delta? What is the inverse transform? The inverse transform?
The range of delta. Delta can be anything, but if you make delta anything, you'll have an overcompletion of operators.
Yes, that's why I'm asking about the inverse relation. How to decompose like the Fourier.
Well, there'll be many ways to do it. It's like you can expand a function in plane waves, or you can expand it in polynomials, or so. Yeah.
What would one basis?
Okay. Well, that would depend on the theory we want, but you know, as Lionel told us yesterday, the S's are the generators of the space of self. I'm going to answer it in a specific theory, but the S's are the generators of the space of self-dual solutions of the Yang multiple. And so they acting on the vacuum, you can generate any solution. So that would be a very natural thing. And in this, the P and Q are related to the conformal weights, and the M's and the M bars are yeah, that would be the P would be the conformal rate, and it runs over the integers 1, 3/2, 2, 5/2, runs over the half integers starting at 1. But that's a very theory specific answer. I mean, in Liouville theory, for example, we can construct operators of any dimension. We can write e to the alpha phi for any alpha. But it's a difficult problem, which has now been solved. What are the independent, what are the independent fields? Okay, so so now I am running out of time. And so let me now turn to so now if you do this, if we do Yang-Mills theory on AdS4, and we have a gauge group G, there will be a global current on the boundary, JAA, of TZZ bar, where this runs over TZZ bar, which is conserved. And moreover, its conformal dimension chi equals 2. Okay, this formula was for reducing scalars to conformal scalars. Here we're reducing conserved vectors to conserved vectors. And so there's more stuff. We have to use the inversion tensor. And 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 what you get is J delta. So I want to write conformal prime of arbitrary weight delta, which will depend on WW bar. And it is, and there's going to be a plus or minus here. And it can be written as integral d squared z dt times 2 t plus or minus I epsilon to the delta minus 2, z bar minus w bar, capital JT, divided by t squared plus z minus w squared plus or minus I epsilon to the delta. And there's one more term involving jz, which I'm not going to write because it's going to end up being 0 for the specific thing I'm going to tell you. So this is now a 2D current of weight delta. Now, let's consider the specific thing, J1. Let's define J1W. So what I'm going to tell you now is what S1 is. And I should have been writing the gauge index here. I'm going to tell you what S1 is. So J1W is J1A W plus minus J1A W minus. And you see that when you set delta equal to 1, you get a pole here. So this t is integrated along the real axis. But if I take the difference between the plus I epsilon and the minus I epsilon, this just becomes integral d squared z dt, contour integral over t. So I have delta I1 is minus 1, and then I have this 1 over t squared plus blah, blah, blah to the 1, and then jta. And so this just becomes, you just have to pick up a pole at t equals 0. This t disappears. You get a 1 over z minus w squared, which turns this into 1 over z minus w. So this just becomes, and I'm dropping factors of 2 pi, d squared z over z minus w jt at 0 zz bar. Now if we take d bar j1 aw, this turns into a delta function, and that is just equal to jt 0 zz bar. Now, jt is 3 dimensions associated with a global symmetry. So we know what its OPE coefficients are on very general grounds. And practically by definition, we have that JTA, that's the charge density, it would be the generator of the global symmetry transformations in 3 dimensions, TZZ bar, with any operator O which transforms under the global symmetry has to be T over T squared. Well, let's write this as T prime W bar. T minus T prime squared. Let's put this operator at 0. So it's just T squared minus Z minus W squared. And FABC OC of O WW bar. This form is completely fixed by the statement that J generates a global symmetry. Now, we want to take this to 0, and it looks like we're in trouble because it looks like it's going to be 0. But this has a power, doesn't it? Yeah, this is to the 3 halves. And because of this power, it's not hard to see that this is actually delta squared z minus w FABCOC. Okay, so if J gets a delta function with any charged field, then big J, then little j, 1A W of W with O B goes like 1 over of ZZ bar, goes like 1 over Z minus W FABC OC. Okay, so this is the definition. Practically, oh, I've got 10 minutes? Oh, darn. Okay. So this is the definition of a 2D Kac-Moody. And see with more work whether this Kac-Moody algebra has a level. A level would correspond to a 2-point function in AdS of 2 positive Felicity gluons. But at least we've found the first piece of the connection between the boundary structures on AdS, where we have towers of holomorphic conserved currents, and sorry, in celestialography, where we have towers of holomorphic conserved currents, and in AdS4, where we just have one global conserved current. And basically, we take the one global conserved current, and okay, the machinery is a little complicated, but we have one global conserved current. We decompose it in appropriate SO3, 1 representations, and those are the SO3, 1 representations. So the meaning, we shouldn't have been looking, or I shouldn't have been looking for soft theorems in AdS. What we should have been looking for in AdS was the thing that was already there, which is what it matches with is the thing which was already there, which are current algebras of currents associated with global symmetries. And I just want to make one final closing comment. So we have this picture here. And we have a bunch of a sphere here, a lot of structures on it, the S algebra, the W algebra, and so on. And so celestialography is the process of understanding what's going on in this picture just from the 2-dimensional things on here. In Carolian holography, you build those back up. You can unravel celestial holography and take towers of SO3, 1 representations in celestial holography and recombine them to make representations of the Carolian group. But you can also, well, at least we've taken the first step, much more been done in Carolian, but you can also, so that recombining in this way would give you Carolian. Recombining in this way will give AdS. So let me stop there, and yeah, so in summary, the soft generators in celestial holography do survive in AdS4 if you map it this way. They're not soft anymore, but of course, energy in Minkowski space is not energy in AdS. And the modes under the SO3 decomposition of the 3D conformal group obey algebras, which look like they're going to be. We haven't shown this, but they look like they're going to be the S algebra. And even more interestingly is if we can, something even more interesting has to happen when we try to do this for gravity, because we have to get out this W algebra out of it. So let me stop there.
Thanks a lot, Andy, for a great talk. Questions?
I can ask like that. You seem to have a general procedure for getting 3D CFTs to 2D series. Can I do general 3D CFTs?
Yes.
With the vector model in 3D, for example, I will find the different dimensional symmetry. How do I know that this comes from self-Florian means and not from just Young-Hills?
Well, I mean, you can do it for any CFT. This formula, yeah, that formula there, it's a little bit too hard to do on a blackboard in a talk, but it's not very hard. You could take this and just view it. It's just you act with the 3D generators on the 3D thing, and then this phi delta has some interesting, you integrate by parts and you act on it, and okay, so that all works. Now, why you would want to do it in general, I don't know. There aren't that many reasons why an ordinary condensed matter or CFT expert would want to do it, but definitely this holography applications, and particularly when we're trying to, relate and extend AdS holography to flat holography and de Sitter holography. We could also, there's actually another direction here. If we do that, we get DS. So here we get AdS, and then we do that, we get DS. And so it's an interesting thing to try to do from the holography point of view. Yeah. Did I answer your question?
Well, how do we know that this theory comes from self-Florian means or from since your procedure seems very general in the boundary? That was the second part of the question.
Yeah, how do we know that it comes from self-Yang mills? Well, because, yeah. So what we need to do, and this is an interesting problem. Yeah, good, yeah, I see what you're saying. Okay, so we start with self-Yang mills on AdS4. And we already know in flat space that we get the S's without the central term. We start from with self-Yang mills on AdS4, and we impose some boundary conditions, and then we systematically figure out what the correlators are, what the operators are, and so on, and then we reduce it and see where we land. Now, this sounds like a straightforward problem and something that somebody who works on AdS could do in their sleep. But in fact, it's a weirdly complicated problem. And at the last celestial holography, there was the thing in New York. This guy Pimentel, Guy Pimentel, said he's been working on this there should be a simple formula for all the correlators in AdS4, like something at least as simple as the Park-Taylor formula, the all plus correlators in AdS4. And people have been looking for it, but it's tricky to define, and it's surprising how hard it's been. Not like hundreds of people. Like there's a half a dozen people who've been thinking about this for a long time and haven't quite been able to do it. I'm hopeful that it's a question of how you organize the calculation. And I think what hasn't really been done is using this algebra to organize the calculation. That's our guess, that the algebra will be the guide to it. It's also very tricky figuring out how self-dual theories in Minkowski space are not CPT invariant. So, you have to complexify something that is not supposed to be complexified. And so that becomes a little tricky as far as what are the rules for AdS, what kind of boundary conditions are consistent with self-duality. A number of questions, which all seem technical, and I think probably are technical, come up. Yeah.
So precisely, these questions will probably become even worse in the case of self-dual gravity, right? And my question is, are you considering linearized version of the self-dual gravity or the full version?
Great question. Well, they'll become worse in some way, but they may also become better because this deformed algebra is so specific. And we know that if we land on that, we're doing something right. So I think this deformed algebra is, we've really got our foot in the door there. Now, of course, gravity, unlike Yang-Mills theory, I think it's going to be more complicated than Yang-Mills. That's why we're doing Yang-Mills first. A theory, you can't have a duality is the thing having to do with gravity. So you can't have a full dual if you're just doing Yang-Mills theory. You have to couple it to gravity. You won't have the boundary theory won't have the operator corresponding to the stress tensor in the boundary theory won't be present if you don't have a graviton. Okay, so ultimately we must do gravity. Now, gravity is not conformally invariant, like Yang-Mills theory, so it's not quite as simple. But the spin 2 wave equation, which is for these chiral algebra generators, the generators are constructed just by using the spin 2 wave equation, and the spin 2 wave equation is conformally invariant. So we can use this trick to lift the W generators from, but the free theory is conformally invariant. So we can use this to lift the expressions for the linearized W generators from flat space to anti-de Sitter space. But clearly there's going to be more interesting things happening when we consider interactions. And the hope is that what those interesting things are has already been solved for us.
Okay, one last question in view of time.
In flat space, to go from self-dual Yang-Mills to full Yang-Mills, when going from self-dual Yang-Mills to full Yang-Mills, you encounter this ambiguity in defining the double soft theorems as well when you study positive and negative helicity soft gluons together. So in AdS4, this decomposition in the circle reps gives you a soft expansion in AdS4. Could somehow turning on a cosmological constant resolve this double soft ambiguity and give you a well-defined way of going from self-dual Yang-Mills to full Yang-Mills?
Well, let me answer your question in gravity. Okay. Very interesting thing. Oh, I guess they're. I guess they're pretty well. But It turns out that, this is really worth saying because it's so beautiful. In this deformed W algebra, the deformed W algebra has a really cool symmetry in which you take P to 1 minus P and Q to 1 minus Q, and you exchange M and M bar. That is, you flip the helicity. So basically, the wedge of, in the wedge for the W algebra, there's also a W bar algebra. So this deformed algebra contains both W and W bar. It in some sense. And in fact, it has the W1 generators, if you go out of the wedge, are like a Virasoro, but the W2 generators are like the barred Virasoro. So I think that this W algebra is telling us, I don't know what it is, but I think it is telling us something very interesting about combining the left movers.